Hello, can you listen me? Hello. Okay, so let us start. So in last class we have seen this winner take all learning algorithm. So today we will see one problem based on this. I just want to revise what we have done in last class. So winner take all is a competitive learning rule. That means neurons are in competition to learn the things while the network is in learning mode. So whenever you are training your network, all the neurons are fighting with each other and the winner will be used for training. So this kind of system is used in coherent network, which is used for clustering. So this is a clustering network. So that means it is unsupervised. There won't be any label to the data. So data will come in raw format to you. You have to make groups of data. So such job is called as clustering. So we have seen the network structure. So this is a network structure with 3 neurons. You can add as many neurons as you want. That depends on number of groups you want to make. Suppose you are provided 100 samples and you want to make say 6 groups, then you will put 6 neurons in a layer like this. Okay, so each neuron here will represent one group. So basically we'll see that at the end of the training, these neurons are representing cluster centroid of respective groups. Say this is say some cluster, and if I make a one group, then the centroid here will be represented by weights of respective neuron. So that you can see here, these are some weights, say W11, W12. So they are associated with neuron number 1. So this is W11, this is W12. So this is weight for neuron 1, which is actually after training will converge to the centroid of group 1. Similarly, these weights associated with neuron 2, they will be converging as centroid of group 2 and so on. So these are actually centroids. So what is purpose here? When you have training done and all centroids, say this is group 1, this is group 2, maybe this is group 3. Say there are 3 suppose neurons in my layer, say these are 3 groups. Now whenever there is unknown sample, say X test appears suppose here, then you will see who is the nearest centroid to this X test. You can observe here that G1 is the nearest centroid, so possibly this X test belongs to G1. So somewhere, suppose I put there X test, then this will be the closest centroid, then this X test possibly belongs to G2. So like that, there will be the final decision for unknown or new samples. Okay. Now we have seen the procedure, how it works. Say, let us go to the steps. Let me clear this, just 1 second. So this is these are the steps to train the layer. say first is normalize all training samples, so that is must. So you will make length of each training vector equal to 1. Okay, so that is called a normalization. I can give you small examples. If this is the vector, training vector, then you can convert into normalized form. Suppose this is called as x1, then x1 cap, which is the normalized version, will be equal to, say, 1 over this 1 square plus 2 square multiplied by 1, 2. So whatever is that vector, so this will be 1 plus 4, 5, so 1 over root 5 and 2 over root 5. So this something like this. So this will be the normalized version of this vector. You can check here what is length of this. It will be equal to 1. Okay, so norm of a vector, that is length of a vector, when it is converted to 1, it is called a normalized vector. Now, first condition is to make this normalize. Whatever training samples are given to you, you normalize it. We will take one example and we will follow all these 7 steps one by one, and I hope you will understand how it works. The second step is randomly assume all weights and again normalize. So this step is again important. You assume a weight matrix which consists of weights of all the neurons, and you take the row number 1, you normalize and put it into the normalized matrix. So then second, then fourth, and so on. So these rows are made intentionally normal. Reason I have explained in last class. So for the given input x, find then W transpose x. You can just multiply this weight matrix by input x. You will get corresponding net vector, which consists of nets of all the neurons in that particular structure. So then you choose which neuron is winning for your input training sample. Say, suppose neuron number 5 is winner, then you will train only this neuron. No other neuron is disturbed, only the closest neuron to the input is selected for training. Then change weights as per our formula and then renormalize. So don't miss this renormalization step in your problems that may appear in your exam, because if you don't follow this, your answer is going to be wrong one. Okay, so this is a must step. Even you can try with your programs in lab. If you remove this, what happens? Then repeat this procedure, say maybe 2 to 6. I should take 2 to 6 for all training samples. Now let us take this problem. So it will be better if you write down this problem with your own hands and get acquainted with the steps. Now what is this? This is called as training data. So this is training data. How many samples are there? So this is, say, set D consists of x1, x2, x3, x4, x5, which is equal to, say, this set. So these are samples x1, x2, x3, x4, and x5. Okay. Now you can see, if I take x1, this first sample. Now what is your problem here? You take these 5 samples, and problem is make 2 groups of above data. Your task is to make 2 groups. Say two clusters, that is k equal to 2. So for that, some data is provided. And suppose I take the first sample, that is x1 equal to 0.8, 0.6. Then first step for me is to check whether this is normalized or not. Normalized or not means I have to check the length of this. So what I do, I just take square root of 0.8 square plus 0.6 square, so that is 0.64 plus 0.36, so it will be square root of 1, which is 1. Okay, so that means this x1 is already normalized. So in this case, all you will see that all these vectors which are provided to you for training are pre-normalized. So you need not do normalization, but when you check it, you can verify that all these are normalized vectors. Okay, everybody has length 1. Okay, you can check that, even this one. So verify that these are normalized. Once all samples are normalized, that means you have completed step number 1. So this will be your first step. Whatever data is given to you, one by one you will normalize it. Now what is next step? Next step is randomly assume all weights and normalize. Now before I do that step, I must see what is the structure of my network, how to design that. Now what is the requirement here? My requirement is k equal to 2. So I want to make two groups. So let us take two neuron first. So this is neuron number 1, this is neuron number 2. If I want 3 group, then I could have taken 3 such neurons. So this will be input like this. So this is x1 and this is x2. So combiningly, this will form input vector x. Now this will be w11, this will be w12, this will be w21, and this will be w22. So this will give you a W matrix, which is W11, W12, W21, and W22. So you can arrange like this. Now what is done here in your problem, these weights are given to you as W1, that is for neuron number 1, 0 here stands for 0th iteration. So we have not done any iteration till now. So for first time, what is provided to us is an assumed, randomly assumed weight. So this is assumed to be 1 0 and this is minus 1 0. Okay, so second step was randomly assume weights, so that is done, and then normalize it. So you can check here whether this is normalized or not. So W1 0, so that is 1 square plus 0 square square root. So this will be length of this, and you will see that this is 1. Similarly for this, minus 1 square plus 0 square, so this is also 1. So both weights are normalized. So two steps are over now. The training samples are normalized, assumed weights are already normalized. So these two steps are over. Now we have to take the first input and find out corresponding output for your neurons. Okay. Now this is my weight. for neuron number 1, and this is my weight for neuron number 2. Now here the learning constant is selected as 0.5. Now what we have to do is we have to take the first training sample, that is 0.8, 0.6, this one. We are selecting this one for training purpose. So net 1 of your neuron is W10 transpose X1. So this will be 10 multiplied by 0.8, 0.6. Okay, so this will be just 0.8. Okay, then you can find out net 2, which is W20 transpose dot X1. So this will be -1, 0 multiplied by 0.8 and 0.6. So this will be -0.8. Now you can do this individually, or you can put this thing into a matrix form. That is, you can write this complete W weights of your circuit in one matrix. That is, for first neuron it is 1, 0, for second neuron it is -1, 0. Okay, and you can directly compute net vector, which is 1, 0 -1, 0 multiplied by 0.8, 0.6. So this will directly give you 0.8 and -0.8. Okay, so this is actually equal to net 1 and net 2. You can directly do in one step, or you can go as I have done here separately. So mathematically, or when you see packages, this will be simpler approach. Okay, so program wise, second approach is simpler one. To understand, this is better one. Now what we have to do is we have to choose who is the winner. So who is winner here? Can anybody tell who is winner? So winner is neuron number 1. So neuron 1, since its output is 0.8, which is max compared to this, so we will choose now neuron number 1 for training purpose. Okay. Now how to train this? We have to use this change in weight formula, which is written on this top. Say right corner, you can see that formula. Now what we will do, we will do this change in weight for the first neuron, because that is the winning neuron, and this will be equal to learning constant is 0.5, 0.5 multiplied by x. So you can go directly with x1. So x1 is 0.8, 0.6 minus w. So w is 1 and 0. So I am doing changes at a time. Okay, this is using vector form, or you can use this formula to change individual weights. So I am doing it in one step, so you can follow this method. So this is 0.5, say multiplied by, so 0.8 minus 1, so this will be 0.2, and 0.6 minus 0, so this will be 0.6, into 0.5. So this you can take as minus 0.1 and 0.3. Okay, so this is change in weight for the first time. Now this change in weight you are going to add with existing weight. So this change in weight will give you the new weight for the first neuron. So this will be W11, which is equal to W10 plus change in weight for first neuron. So this will be equal to 10 plus now minus 0.1 and 0.3. Okay, now when you add this, so this will be 0.9 and 0.3. So this is my modified weight after presenting the network the first training sample. Now what is next step? If you see, so we have done this change in weights. Now sixth step, don't forget this, to renormalize. Now you can check here what is length of this vector. So this vector length is 0.9 square, so 0.81 plus 0.3 square, so it is 0.09. So its length is equal to 0.9, square root of 0.9. Am I right? Is this fine? Okay, so this is not equal to 1. Okay, so this is not equal to 1, so we need to renormalize. So renormalize this weight. So what we can do is 0.9.3 multiplied by 1 over 0.9 square plus 0.3 square. So if you do this step, this weight, updated weight, will be renormalized and it will be equal to this. Okay, now after renormalization you will see these weights for neuron number 1. Remember, we have not played with or handled or changed weight for neuron number 2. So after presenting the first input, what is my weight matrix now? Okay, if you remember the earlier one, the earlier weight matrix was, let us say, W0, then this is 1 0 and minus 1 0. So this was earlier one. Now that will be changed to 0.948, 0.316 and minus 1 0. So remember, second row we have not disturbed. Since winner was first neuron, so we have changed only this much. Okay, so this is the updated weight after first training sample. Now what is next? So we have reached this step. Then what we will do? We will do updation for second training sample. So this we will take and we are going to repeat whole this procedure. Okay, so if I do this one by one for all the training samples, okay, and iterate over a period of time, then you will see that, say, after around 20 odd iterations, you will see that your uh, weights are getting stabilized to 3 locations. You can see this is the weight, final weight for first neuron, and this is the final weight for second neuron. Okay, so they are getting stabilized at this 2 locations. Sorry, this is not final, this will be the final. So this is the final location for neuron number 1, and this is the final location for neuron number 2. So you can see that there are patterns x1, x3, x5, they are grouped together, and there are 2 patterns like x2 and x4, they are in one group. So these 2 samples are kept in one group and represented by this center vector. So it's like a mean vector for these 2, and this vector, which is the neuron number 1, is representing 3 patterns, that is x1, x3 and x5. Now you can look at these samples and compare with this diagram. Now we are in group x1, x3, x5. So let us see what is x1, x3, x5. So this is x1, this is x3 and x5. Okay, so they are looking similar. It is 0.8, 0.6, 0.6, 0.8, and this is 0.7, 0.7. Now when you check with the second group, so this is x2 and this is x4, you can see that they are close to each other. So it is 0.17 and this is 0.34. The second position is minus 0.98, here it is minus 0.93. So they are similar patterns. So these similar patterns are kept in the same group. So that is beauty of this network. So it is automatically finding out who is close to who. Okay, so after iterating over a period of time, so these groups are formed, and you can check that the mean of, or the average value of x1, sorry, x2 and x4 is this vector, which is the weight of neuron 2, and the mean value of x3, x3, x5 and x1 is represented here as weight of neuron 1. Okay, that is what I said at the beginning. Now if you have one more, say, neuron, then, and you must have those many samples, then you may have the third group somewhere here depending on your data. So like that you can make any number of clusters using this technique. Now what is minimum? As I said, you must have minimum 2 groups. How many maximum you can form is equal to number of samples. So number of samples you have, you can make those many groups. So that is how this will work. Now the next part of this is the counter propagation network, which is basically a combination of 2 layers. So this is Cohen layer that we have seen right now, which is based on WTA algorithm, that is winner take all, and there is a Grossberg layer which is here. So this requires Outstar learning rule. This first layer requires winner take all learning rule, and the second layer requires the Outstar learning rule. So what is that? Now, before I go to what is Outstar learning rule, let us see the practical situation when you use this practically. What happens is, since we are assuming weights randomly for all these neurons, say 1 to, let us say k, then we don't know which neuron is representing which group. Say for example, I have data for numbers 0 to say 9. Some data is with me, and I have divided this data into 10 groups using this network. Now I want to see that whether this network is able to produce, for suppose digit 1 at this position, it should produce say maximum response. For digit 0, you will get max response here. Is it possible to get such kind of output using WTA? So answer is no, because we randomly assume weights and we don't know when I apply a feature of 0, or we cannot ensure that this will be the winner. Okay, so there is no guarantee. Maybe for the first digit 0, if I apply 0 here, then maybe this kth neuron is winner, or maybe 5th neuron is winner. Okay, so this winning order is not in our hand. So it totally depends on how your random things are appearing as weight to these neurons. Okay, so to make this thing in order, so this output is randomly ordered, and I want that all the outputs are in proper order. That means if I apply a feature of say 0 as input, then this will be representing, or this neuron will represent digit 0. This neuron will represent 1, and so on up to 9. Okay, so like that I want a proper order of output, but here order is random because I assume weights are random. So what we do, we have a WTA layer which is trained as we have discussed in last step or in last class or till now. Then what we do, we completely finish off the training here for WTA, and then we take a second rule, that is Outstar learning rule, to make the things in order. So this is an optional network. You may use this, you may not use this. So this is a way I am explaining how you can do this using neural network. Otherwise, you can use this first part for your job. So this is completely fine. If you don't want this ordering, you can even still use this. This is the optional part. Okay, now anyhow, how to do this? So what we do is, we take the winning node from previous layer. So this is the winner, suppose. Now the connections which are going away from this, so these are the highlighted connections here. Weights associated with these connections are only trained. Okay, so this is fan out kind of a situation. So from winning node, whatever connections are going ahead, they are getting trained for the proper order. Say for example, I am applying input here, which is digit 0, and say this is the winner. So this neuron is winning. So this is representing 0, but I want this max output to be here at the first position, not here. So what I do, I apply my desired response like this. Say this is 1, 0, 0. So this becomes my desired vector for this input. Okay, and then based on this desired response, I update weights over here. Okay, so the rule to do this is change in weight. So Outstar learning rule is change in weight is equal to some learning constant C desired response minus Wj. Okay, so Wj stands here for the weight associated with jth input, not neuron. Okay, weight associated with jth input node. So weights associated from this jth input node are going to different neurons. So this is a different situation compared to earlier one. In WTA, we were selecting winning neuron like this, and weights coming from different inputs to this say neuron, winning neuron, they were updated. So they were coming from different inputs like this. Okay. Now here situation is totally different. You have some winning node here, which is a jth node from this layer, and there are connections which are going to different neurons from this jth connection, and the associated weights here, they are getting updated, which are connected to different neurons. So this is fan in situation and this is fan out situation. Okay, so you can make a separation of this two. Now if you use this Outstar learning rule, then you can have proper ordering of your output. Okay, this is the input, say 0, then this will be winner. If I apply then feature of digit 1, then this will be winner, and so on. So like that, if I apply digit 9, then last node will be winner. So this is the Outstar learning rule. So here we come to the end of learning rules. We can quickly revise what rules we have seen till now. So we have seen Hebbian learning rule. Then we have seen perceptron, Widrhoff, delta, correlation, winner take, and Outstar. So these are basic rules that we are going to use here onwards. So if you compare this, the Hebbian learning rule is of the form unsupervised. The rule is COX, and we need to have initial weights around 0. So that is the requirement of Hebbian learning rule. You can have any characteristics function as activation function for this neuron, Hebbian neuron. So this is applied to only neuron. So it's not for a layer. So basically it is designed for a neuron. Then second rule is perceptron, which is C into D minus output into X. So this is output, where output is a sine function which produces output +1 or -1. So remember, for perceptron, output is +1 or -1 since we are using sine function. It is not mathematical sine function, it is sine of a number. So suppose I write -5 sine of that, so it will be -1. If I write +5, then it will be +1. Then here you can have any randomly assumed weight, so there is no restriction. So this is a supervised learning rule because D is coming into picture. So whenever you supply desired response, rule becomes supervised. Okay. So it is again applicable to neuron. So you can use binary bipolar or binary unipolar. So that is allowed here. Then third one is the delta learning rule, which is somehow the modification of perceptron. Here you can compare f dash is coming into picture, and you can have any initial weight. It is again supervised. Remember, activation function must be continuous so that it will be differentiable. Again, it is applicable to a neuron. The fourth one, which is very similar to these two, or you can say it's a modified version of delta with the activation function as linear activation function. So if you do that, then you get Woodruff learning rule, which is applicable to any initial weight, supervised, any characteristics function is fine for this neuron. Okay, applicable to neuron. The fifth one is correlation, which is CDX. So this is also called as supervised Hebbian. You can compare both. Hebbian is COX, and here O is replaced by D. So this is a supervised version of Hebbian. So it is applicable to any characteristics function, and it is applicable to neuron, singleton. Sixth, we have seen winner take all, which is applicable to a layer of neurons only. So this you keep in mind. Activation function must be continuous and it is unsupervised. That means it is used for clustering. Seventh one is optional, as I said, is for just the purpose of reordering the things. From this previous step, you can order the things if you want, then use Outstar. Again, it requires continuous, supervised, and this is important thing. You must initialize your weights 0, okay, or near to 0. Then it is again applicable to neurons. So this is in a nutshell what we see as the basic activation. So activation functions and basic learning rules for the neurons. So in next class, we will see different problems based on this theory that we have seen. And next to that, that is on Tuesday, we will have a quiz of 10 marks. Okay, so be ready for that. Let us stop.